In this section, we are going to discuss about the transformation of the independent variable. So let us consider a continuous time signal x of t. Now this continuous time signal is dependent on the variable t, which is time in our case. So this is referred to as the independent variable. So independent variable meaning that it is free to change its value accordingly, or in another way we say as time evolves we look for the changes in the signal activity. So what we're going to do in this particular section, we are going to modify this independent variable and look for the corresponding change in the signal. Now if we have a discrete time signal x of n, then we are going to modify the discrete time represented by n in this case. We're going to familiarize ourselves with some of the most important laws of elementary signal transformation, although this is not going to be a complete list of all the transformation that is present out there. We're going to consider the most important ones, as they will be very helpful in characterizing some of the other important and richer class of systems which we'll be encountering in the later part of the course. The most basic and a very important transformation that we will be performing on the independent variable of the signal xt or xn will be a time shift. So we are going to shift the time by some amount, and we will see how the system or how the signal is going to respond based on the new transformation. Then the second one we'll be talking about is the time reversal. So we'll check out when the time is reversed how the signal is going to characterize. And we will also talk about time scaling. We're going to scale the time and we will see how the signal is going to react based on the new scaled transformation. So let us begin with the first type of transformation, and that is time shift. Let us try to understand the transformation of the independent variable where we are going to time shift it. What is the meaning of time shift? Let us understand with the help of an example. We are going to consider a discrete time signal. It's given by x of n. Now, we are going to do a time shift here. That simply means the transforming the time variable, the independent variable which is time n denoted by n, we will replace it by n minus n naught. So this particular signal now represents a time shifted signal. Now depending upon the value of n naught here, we will get two types of a time shifted signal. One could be a delayed version of this original signal x of n, and the other will be an advanced version of the signal. So what does that mean? A delayed version and an advanced version. Let us check it out with the help of an. So here we have a discrete time signal x of n. Now for different integer values of n, this has got different values. Now what we have done here, that x of n assumes the value which is represented by the yellow color at n equals to 0. So this is going to be our reference value. So we are going to shift this particular signal x of n to the left or to the right relative to this yellow color. So let us begin by first doing a right shift. So doing a right shift means we are going to move the signal first 1 unit to the right, then another 1 unit to the right, and then 1 more unit to the right. So this is the new position of the signal x of n. Now we have seen that the signal is now present at n equals to 3. So this is the value of n naught. So this is a new value. So that means our signal value is now xn minus 3. So we can say that whenever the value of n naught is positive 3, or we can say greater than 0, then this represents a represents a right shift. This is a right shift, or we can say this is the delayed version of the signal. Now, what is mean by the delayed version? The delayed version of the signal. Now we know that originally the signal was to start at n equals to 0. Now delayed means instead of starting at n equals to 0, as shown by the reference marker point, which is the yellow color, so it is starting from n naught equals to 3. So it is starting 3 seconds later. So that's why it's a delayed signal. Now let us bring back the signal back to its original position. So we have it in the original section. Now what we're going to do, we're going to shift the signal to the left hand side. So let's make a shift of 1 unit to the left, then another unit. So we see that the signal is now at n equals to -2. We shifted by another 1 unit, so the signal is now at n equals to -3. And finally we do a shift by another 1 unit, so that the final position of the signal is at n equals to -4. So this is actually the value of n naught. So here we have n naught is equals to -4. So we do a shift. We have shifted the signal to the left hand side, so that means we have the signal represented by x of n minus of -4. So that gives us x n plus 4. So this is now the advanced signal. Now advanced in the sense, now this has started earlier. The signal was to have started at n equals to 0, but now instead it has started at n equals to 4. So this is what is meant by a time shift. And also this will be the cue point, so that whenever the value of n naught is negative, so that means it's a left shift, or it's an advanced signal. So let's draw both of the advanced version and the delayed version of the signal, and that should give us something like this. So we have the signal x of n, time shifted to the left hand side and time shifted to the right hand side by 3 units. Here we observed that the delayed as well as the advanced version of x of n are identical in shape. Even though displaced or shifted relative to each other, the shape remains the same. So we can do a time shift for a continuous time signal as well. So assuming that we have a continuous time signal given by x of t, so when we do a time shift, so the new function or the new signal becomes x of t minus t naught. So depending upon the value of t naught, we can get either an advanced version of xt, or we will get a delayed version of x of t. So that means when the advanced version would mean, for the advanced version, the value of t naught will be less than 0, and it is a left shift. So that means our signal has moved to the left without the change in its shape. So this will be the advanced shift. Let's bring it back to our original position, and the shift to the right will mean that the signal is delayed by t naught amount, and that will be given by the delayed version will be given by t naught greater than 0. So this will be a right shift. The second transformation of the time axis that we will discuss right now will be the time reversal. So time reversal means, given a continuous time signal x of t, when we do a time reversal, it means we are changing the value of t from positive t to negative t. So let us understand this with the help of an example. Let's say we have a continuous time signal that looks something like this. So when we do a time reversal, then the time reversed signal, which will be x of negative t, can be obtained by reversing the given signal x of t by taking its reflection. We'll take the reflection about t is equals to 0, and that will look something like this. So this is the time reverse signal of x of t. Similarly, we can find the time reverse we can do the time reversal for a discrete time signal, and that will be, if given a discrete time signal x of n, then what we're going to do, we are going to reverse it by changing n to negative n. The best way to understand time reversal is by taking the help of a audio sample. So here I have recorded an audio sample. So the first section represents x of t. The second version is also the x of t, but we will talk about it a little later. So first let's listen to the first part of the audio, and that will be, we are trying to understand the meaning of time reversal. Now what we're going to do, we're going to consider the second part of the audio. This is the same as the first part. So here we select it, and then we are going to reverse it. So this means we have reversed the audio, and let's listen to this new audio sample, the reversed audio version of the original signal. So this is the reversed version of the original signal x of t. So it's simply the audio that is played in reverse order. The third type of transformation of the independent variable time will be time scaling. That means let us consider a continuous time signal x of t. So when we do a time scaling, it means we are changing the independent variable t by some factor alpha. Now we can consider different values of alpha. So let's say for alpha value to be equals to 2, that gives us x of 2t. This means we have doubled the time. So doubling the time means we have speeded it up. And we can have another case where we are considering alpha value to be equals to half. So we have scaled down the time by half units. So that means it has slowed down. Let us understand this with the help of an example. So we have our original signal x of t. Now when we scale it by alpha equals to 2, then it becomes shorter, the duration becomes shorter, because the time is now more faster. It will complete in a shorter duration of time. Well, when the scaling factor is half, then we can see that the time duration between the signals, so this is the time duration, this increases because now the time is longer. Similarly, we can understand time scaling for discrete time signals as well. So xn, the scaling factor, if it is alpha, then this will become x of alpha n. Let us try to understand the meaning of time scaling with the help of an audio sample. Here we have 3 audio samples that are identical to each other. So we'll play the first audio sample. Let's hear it out. We are trying to understand the meaning of time scaling. Now we're going to select the second audio sample, which is identical to the first audio sample, just that we are going to scale it. So scaling means we are going to change the time. So we are going to multiply it by some factor alpha. So for this particular audio sample, we are going to scale it down. So we are going to divide it by 2. So divided by 2 means we have to scale it down to negative 50%. So that means when we are dividing the time by 2, so that means the duration of the time must increase. So let us look at the waveform. So as expected, the duration of our audio signal has increased. Now let's hear this out, how it sounds.
We are trying to understand the meaning of time scaling.
Now let us go to the third audio sample, which is also identical to our original audio sample. Now we are going to scale it up. So we select the audio sample and then we change the tempo of the signal. Now previously we have scaled it down to negative 50%. Now we are going to scale it up to positive 150%. That means we are multiplying the time by 1.5. So when we are multiplying the time by 1.5, that means the time has increased. So increasing the time means the duration, the length of the audio sample must decrease. So let's check out the waveform. As expected, the duration of the waveform is now shorter than the original waveform. So now let's hear it out, how it sounds like.
We are trying to understand the meaning of time scaling.
Let's hear it once more.
We are trying to understand the meaning of time scaling.
So this is the meaning of time scaling. So we have discussed about the transformation of the independent variable, that is time, for a given signal x of t. So we have talked about time shift, we have talked about time reversal and scaling as well. So what will be of utmost interest here is, given a signal x of t, we can do a transformation to this particular signal. Let's say this is a transformation to this particular signal, and this gives us a new signal which is of the form x alpha t plus beta, where alpha and beta are going to be some real values or some scalar values. When you do such a transformation, the shape of the new transform signal will be identical to the original signal x of t. Only exception that will be found will be if the value of alpha is less than 1. That means if the absolute value of alpha is less than 1, then the signal will be linearly stretched. If the value of alpha is greater than 1, if the absolute value of alpha is greater than 1, then the signal will be linearly compressed. If the value of alpha is less than 0, that means if we get alpha as a negative value, then the signal will be reversed in time. And finally, the value of beta. So for any non-zero value of beta, we will get a time shifted value. We will get a time shifted signal, which will depend upon the value of beta. Let us understand this with the help of an example. So here in this question, we have a signal x of t as shown in the figure. So it has a value of 0 for t less than 0. It has a value of 1 between 0 and 1, and between 1 and 2 it is linearly decreasing. Now what we have to do, we'll have to find out the value of x. Value in the sense we have to find out how the graph of x t plus 1 looks like. So our signal x of t plus 1 can be rewritten as t minus minus of 1, such that the value of t naught is equals to negative 1, and this is less than 0. So that means our signal xt will be shifted to the left. So this will be a left shift by 1 unit. So let us shift the signal to the left hand side by 1 unit, and this is how the signal x of t plus 1 will look like. So now that we have the value of x of t plus 1, we can also find out the value of x of negative t plus 1. So we can obtain the signal x of negative t of negative t plus 1 by replacing, we just have to do replace t by negative t into this particular graph and then reverse it graphically. Reverse it graphically in the sense we will draw the reflection of this particular graph x of t plus 1 along the y-axis. So let us do it. So you can say x of negative t plus 1 is the time reversed version of x of t plus 1. So we'll try to draw x of negative t plus 1. So we'll have from negative 1 going to 0 linearly, and then we have a value of 1 from 0 to 1, and then it goes to 0 at t equals to 1, and that stays at 0 for t greater than 1. So this is the time reversed version of x of t plus 1. So this is x of negative t plus 1. Let's also find out the scaled version of x of t. Let's suppose that we want to scale the signal xt by a factor of 3 by 2. That means we want to determine how the graph of x 3t by 2 looks like. So in order to plot the graph of x 3t over 2, so let's begin by first finding out how the signal x scaled by a factor of 3 looks like. So we have x 3 of t. So 3 of t means we are multiplying the time by 3. That means we are speeding up the time. So speeding up the time means the duration of the signal must decrease. So that means our signal will now be of shorter duration. So that would mean that it will have a value of 1. So earlier in the original signal it has a value of 1 from 0 to 1. So this time it is going to have a value of 1 from 0 to 1/3. Then between 1 and 2, when time for time between 1 and 2, the graph or the signal decreases linearly. So here also it is going to decrease linearly, but the duration will be shorter. So instead of having a 0 value at 2, this will have a 0 value at 2 over 3. So this is the value, or this is the graph of x of 3t. Now we'll consider this particular graph, and then let's change the color back to white. So we have x of 3t. Now what we are going to do, now we'll consider the graph of x of 3t and scale it down to a factor of 2. That means we are going to divide it by 2. So dividing the time by 2 is going to increase the duration of the time signal. So that means the graph will now will have a longer duration. So let us draw the graph having a longer duration. So this will be of longer duration. So it starts at 0. So between 0 and 1 over 3, the graph x of 3t has a value of 1. So now since it is of longer duration, so it will have a value of 1 between 0 and 2 times of the previous value. So that will become 2 times of 1/3 will be 2/3. And similarly between 1/3 and 2/3, the graph x of 3t was linearly decreasing. Now this graph is also going to linearly decrease, but the time duration, the time will be between 2/3 and 2 times of 2/3, which will be 4/3. So this is how we have transformed. This is the direction of transformation. Now let's say we want to finally transform x of 3t over 2 to in such a way that now we have a time shift. So let's do it -1. So since it is -1, so we see that the t0 value, so this is our t0 value, which is equals to 1, and this is greater than 0, so that means it is going to be a right shift by 1 unit. So our graph will be now shifted by 1 unit to the left. So from 0, so at 0 the value is 1. Now it will shift to the right by 1 unit. So at this is 0, that 1. So between 0 and 1, the value of the signal will be 0. So at t equals to 1, so it will have a value of 1. Now the time 2 by 3, the position of the time 2 by 3 will get shifted by 1 unit, so it will be 2/3 plus 1. So the function will have a value of 1, going from 1 to 1 plus 2 over 3, which is equals to 5 over 3. And the graph or the signal decreases linearly between 2/3 and 4/3. So that means now this will decrease linearly between 1 plus 2/3 and 1 plus 4/3, because it has shifted to the right by 1 unit. So 1 plus 4/3 is equals to 7/3.